Sorry for the delay. In section 9.3, here's what we're going to do. We're going to transition from hydrostatics, which is what we're looking at, which is water, right, hydrostatics, not moving. We're going to look at water that wasn't moving now to water that is moving, or fluid that is moving. So we're specifically looking at hydrodynamics now. We're going to take a look at some principles that will help us to understand fluids in motion. 4 definitions. First, laminar and turbulent. You've heard it before. You've all heard it before. Have you ever heard turbulence?
Yep. Airplane.
Airplane. Okay. Now, laminar flow simply means predictable, smooth flow. So the particles move in a predictable fashion. They move next to one another. Okay, and I'm going to show you a quick simulation of this in a moment so you can see it a little bit better. Turbulent flow, the flow of the actual particles, whether it be a fluid or a liquid or gas fluid in general, it may start to swirl, what are called eddy currents. Anybody ever go whitewater rafting or canoeing or kayaking or something down a river?
After the hurricane, I went down the river in a little boat. Not exactly.
What you've done? Okay. Ever go past a little rock? Behind a rock, you see little swirls. They're called eddy currents. E-D-D-Y. Eddy currents. And of course, they are little areas of turbulence, but not much turbulence there. Now, on an airplane, what's happening is you have a boundary layer, and the flow over the airfoil, which is the wing, right? The flow over the airfoil is usually smooth. But when it's not smooth, you get these little ripples. Those little ripples there, they end up causing a little bit of a shake. And then the plane has to readjust the flap on this side to counteract that shake. So turbulence, or a flight, is really a battle between turbulence and some sort of, not laminar flow, but turbulent flow and a control system mechanism. In engineering, you design control systems that are able to counteract any sort of fluctuation. So you have this little eddy current, or this little turbulent flow that causes a little maybe lift. So this flap has to change its angle to counteract, to lift back up. That's really what's physically happening there. Before I get to viscosity and ideal fluid, I'm going to pause for a second. So there are several things that affect laminar and turbulent flow. Let's first talk about what's called viscosity to discuss that. Viscosity is the amount of internal friction within a fluid. It's like how much the friction resists itself. For example, you have a faucet, you open it, water flows out pretty easily, right? What if in that faucet, instead of water, it was maple syrup? How would it flow out? It'd be a lot slower, first of all, right? A lot slower. Because the friction between the molecules of maple syrup have a lot of friction, is very high. There's a lot of what's called shear stress. The layers of fluid want to move over each other. Fluids move in layers. The layers want to move past each other. Maybe the layers want to move together. But in a fluid that is very viscous, there's a lot of friction between the layers. So the fluid itself cannot move very easily. Now imagine, instead of just you pour syrup out of a container, it's very easy to see how thick it is. Imagine you had syrup moving in a pipe. That syrup's not even going to move at all, really. You need a ton of driving force to get it to move. A lot of pressure. There'd be a lot of friction between the actual layers of the syrup and the layers of the inner wall of the pipe itself. So viscosity is a measurement of the fluid's internal friction. Internal friction. Something that is high viscosity moves very slowly. Okay, very slowly. An ideal fluid is a type of fluid, God bless you, that we model fluids after that we use. An ideal fluid cannot be compressed. It is not considered to be viscous at all. And it is not turbulent in its flow. Okay, it is not turbulent. Why may we assume everything is ideal? Because most refrigeration and heating applications involve ideal fluids. Now, if that fluid is say it's liquid, and it's evaporated into a gas, and the gas goes into a compressor, like an air conditioner has a compressor in it, the gas, God bless you, could be compressed back into a fluid. But the fluid itself is usually a liquid that we're talking about that's incompressible. Okay, an ideal fluid. Now, there's a term. There's a term called the Reynolds number. Reynolds number is an indicating factor of whether or not a fluid flowing will be turbulent or laminar. There's a limit. If the Reynolds number is greater than the limit, you have turbulence. And if not, you have laminar flow. Now, that number, that limit, is not the same for all fluids. Okay, so based on the fluid you have, there's a lot of properties involved. The density, the viscosity, the velocity, the cross-sectional area, if it's internal flow. A lot of things go into calculating what is called the Reynolds number. A lot of things. We're not going to go into calculating Reynolds number, but you should know that the Reynolds number is your indicating factor of whether fluid flow is turbulent or laminar. It's turbulent or laminar. Okay? Let's go to the next slide. Somebody read that nice and loud for me. Seagrex, please. Rough the board if it's not loaded on yours.
A fluid flowing in a fluid has a constant volumetric flow rate,
So volumetric flow rate. What is volumetric flow rate? What does that mean? What does it mean? Ever take your thumb, put it over the end of the garden hose, what happens? Sprays with higher what? Velocity. Velocity. Let's talk about pressure in a minute. Hold on. For a second. So you put your thumb over the end of the hose, you start spraying a lot more velocity. The reason is the same volumetric flow rate is still flowing, but in a smaller area. Think about it for a second. If I think of water as little cylinders, look at the cylinders in this diagram. Those cylinders have the exact same volume. It's the same amount of volume moving in the same given time period. Volumetric flow rate. So when you put your thumb over the end of the hose, the same amount of water still wants to come out. But you're putting your thumb over the end of the hose. So there's a lot less area. I can't have the same flow, right, the same velocity in a smaller area and assume that the same amount of water is going to come out. It's not possible. The only way the same amount of water, the same rate of water could be coming out would be if the velocity increased a lot. So look at this diagram. In the second location, the area is bigger. The area is much bigger in the second location. So you could expect the velocity to be what? Slower or lower, yes. Okay, and take a look at the continuity equation right here. This is what tells us the truth here. If A2 goes up, V2 has to go down for A1, V1 to be a constant. Okay, remember that the fluid flowing in a pipe has a constant, that's the key word, flow rate. So if this isn't changing, it means that A1, V1 is the same. But if I suddenly double the area, well, then I have to have half of the velocity. Okay, for this to hold true still. If I double the area, the velocity needs to halve. How are these related then? What's the word? Louder? Indirectly related. Indirectly related. Okay? Let's do a mathematical example. Be careful. The answer is not 2. The answer is not 2. Almost everybody in the last class voted for 2 as the answer. Try to figure out why it's not just 2. I did, I'm sorry. But I'll make it a challenge for your class then. Why isn't it 2 is my question to start with. So read the question. We have water flowing through a pipe. The radius is 4 centimeters. The velocity is 5 meters per second. We want to double the velocity. So the question is, what do we do to the radius? Most people said make it 2, right? Have the radius, you double the velocity. Indirectly related. Why isn't that true? What is it? The units? What do you mean? Doesn't affect it, no. Good idea though. Paul?
Would you have to increase it by a factor of 4?
No, but you're on the right track. The idea of what you're saying.
shouldn't the radius the
Nope.
velocity. No. The air. Never mind. I take it back.
What's that?
No, I take it back. I don't know what I said.
No? Jenny?
Take the radius, because it's a circle.
Yeah, guys, we're given the radius. What did the continuity equation relate? Area and velocity. How are area and radius related? Area equals? Yeah, so it's r squared, which is going to throw us off. So let's take a look at this now. Here's the continuity equation. Area is really this. Agreed? 1 and 2 signify one location, second location. Now, if this is true, cross out your pi's, obviously. Pi cancels. Clearly here, if I double the velocity, I can't just have the radius, because they're not indirectly related. They're indirectly related to the square of the radius now. So let's take a look at this one mathematically and see what our answer turns out to be. So we know that the initial radius is 4 centimeters and the initial velocity is 5 meters per second at the first location in the pipe. So R1 I'm going to plug in. R1 is really 0.04 meters. Times V1, which is 5. What should V2 be? What should it be? Why 10? Somebody else? Why should V2 be 10? You're what? You're doubling the velocity. That's the goal. So I could look at this. I could solve for R2 and I can get an answer. I'm going to tell you the answer because I want to talk about it for a moment. The answer you're going to get is 0.028 meters, which is 2.8 centimeters. So we started with a 4 centimeter radius pipe, and we're not half of that now. We're at 2.8. We're at 2.8. Take 4. Take the number 4, please, on your calculator. Divide by the square root of 2. What do you get when you divide 4 by the square root of 2? 2.8. Not a coincidence. Let's discuss why. Take this equation up here, and let's rewrite it. See what I'm doing? Take the equation up top, please. Rewrite it at the bottom. Now, if I solve this algebraically, I could clearly prove that it decreases by a factor of radical 2. That's why I had you divide by radical 2. Let's prove that. The second velocity should be double the first. So replace V2 with double V1. I put it in red so you can see it. Again, the second velocity should be double the first. So instead of putting a 5 and a 10 here, I'm going to put double V1. V1 is on both sides, and it's all products. So what happens? Cancel. And it's always products, you cancel. Or factors, I should say. How do I get rid of that 2? That's multiplying. So I've got R1 squared over 2 now equals R2 squared. How do I get R2 by itself, which is good? Square root both sides. When you square root both sides, this becomes, again, radical R1 squared over radical 2 equals R2. Remember, this radical is on the whole thing. I'm going to break it up into 2 pieces. What's the square root of R1 squared? So it becomes R1 over exactly what you did to check the answer. Okay? So algebraically, you could see a lot more power in this than if you just plug in numbers. So it becomes R1 over radical 2. So you take 4 divided by radical 2, you get 2.8 centimeters. Very, very useful for those of you that struggle to finish your test quickly. Okay, if you recognize this fact, that this is able to sub in, you might want to use your variables this way, especially if it's multiple choice, and coming up with a number getting 2.8 and then saying, oh gosh, how do I get from 4 to 2.8? What did that decrease by? And you'd have to try all the chances. It decreased by a factor of radical 2, it decreased by a factor of 2, it decreased by a factor of 4, or it increased by a factor of radical 7. Who knows? You know what I mean? So doing it algebraically may help you. For those that are thinking about the subject test, definitely consider algebraic approach here. You're probably not going to be given numbers. You didn't have to be given the number 5. Notice we didn't use the number 5 anywhere. The velocity of 5 meters per second that we used earlier, we did not use it just now. We replaced, right? We replaced this V2 with double V1 instead of putting a 5 and a 10 here. So you really didn't need those numbers. The 4 you definitely need. Okay? Well, if it's multiple choice, you don't even need the 4. You could say the radius decreases by a factor of radical 2 without even having the 4 centimeters involved in this problem. Okay, so you don't really need numbers in these problems, as we've seen before. Bernoulli's principle tells us that the pressure in a fluid goes down as the velocity goes up. So those are what related? Okay. The pressure decreases as the velocity increases. So take a look at this nozzle you have here. It's a nozzle. It's like a fire hose. At the end of a fire hose, you can tighten or adjust the cross-sectional area. Why might they do that with a fire hose? Why might they close off the area a lot? What would happen to the water? It would shoot a lot faster and further. You get the same volume out, but if you're a firefighter, you need to get to the 3rd floor or 3rd story, you might want to tighten up that nozzle so the water flies a lot further. Okay, this is an example of a nozzle. It's a tapered, you should know that word by the way. It's a good vocab word for physics or for anything in science. This is a tapered, T-A-P-E-R-E-D, a tapered cross-section. A tapered cross-section is like a baseball bat. You have the barrel and you have the handle. How do you get from the barrel of a baseball bat to the handle? You have to have it be tapered. The cross-section has to go down. Okay, the cross-section has to go down. Now, if I want the velocity, in this case, if I'm looking at it, we talked about this a moment ago. When the cross-section goes down, the velocity goes up. The velocity goes up. So over here, P2, okay, is less than P1. Again, the velocity at this location has gone up, so the pressure has to go down. So the pressure here is greater than the pressure here. These pressure gauges are trying to show that in this diagram. The pressure is greater right here than it is right here. So what happens is you have a pressure that is higher behind the nozzle, lower after the nozzle. If there's a difference in pressure, there's a difference in force. If there's a difference in force, there's acceleration. If there's acceleration, there's a change in velocity. That's why the velocity changes in a hose when you put your thumb over the end. That's the reasoning behind it using pressure terminology. Let's take a look at an application of Bernoulli's principle. An application of this. Mike, why don't you read it for us, please?
The force on an airplane wing can be explained using Bernoulli's principle. Airplane wings are designed so that the airspeed above the wing is greater than the airspeed below the wing. As a result, the air pressure above the wing is less than below the wing. This imbalance of pressure creates a net force in the upward direction known as the lift force.
So you've heard the term lift force before a lot, but the lift force literally means that you have a pressure differential. So what happens is this. The airfoil is designed so that the velocity on top is greater. And as a result, the pressure on the bottom is then greater. Remember, velocity and pressure are inversely related here. So if the pressure below the wing is higher than above, you have more pressure, it's going to push it up. So you have this net force lifted upward. This lift force, F, is shown in the diagram. If the lift force exceeds the sum of the drag force, it's not a linear sum, it's a trigonometric sum. If it exceeds the sum of the drag force and the weight of the plane will then lift off. If this lift force does not exceed those two, it will not lift off, or if it's in the air, it will end up crashing. Okay, so the concept behind lift force uses Bernoulli's principle and a pressure differential. Okay, a pressure differential. The whole idea is having a higher pressure below the wing causing it to lift off the ground. Tonight from this section, remember that you have 9.2 as well.